Have you ever been caught in a massive crowd, perhaps at a concert, a busy train station, or even during an evacuation? Understanding how large groups of people move isn't just fascinating, it's critical for safety and efficiency. From designing safer stadiums to planning evacuations, knowing how crowds behave is key. And surprisingly, mathematics plays a huge role in deciphering these complex human flows. Scientists use different mathematical strategies to model crowds. Think of them as different lenses to view the same phenomenon. First, there are microscopic models. These zoom right in, focusing on each individual person. It's like simulating every pedestrian with their own destination, desired speed, and how they react to others and obstacles. A famous example is the social force model, which treats people like particles influenced by forces, attraction towards their goal, and repulsion from things they want to avoid, like walls or other people. These models are very detailed, but can require a lot of computing power for huge crowds. Then, we have macroscopic models. These zoom out, treating the crowd more like a fluid. Instead of tracking individuals, they look at overall density and average speed in different areas. They use equations similar to those used in fluid dynamics. These models are less computationally heavy and great for seeing the big picture, like where bottlenecks might form in a large area, but they don't capture individual actions. Finally, mesoscopic models try to bridge the gap. They group people based on certain characteristics, like where they're going, offering a balance between individual detail and large-scale flow. What kind of math powers these models? Differential equations are key for describing how positions and speeds change over time. Cellular automata use grids to simulate movement between cells. Optimization helps find the best evacuation routes. Probability and statistics account for the randomness in human behavior, and network theory can view spaces as interconnected paths to analyze flow. Lately, artificial intelligence is adding another layer. Deep learning helps models learn realistic movement patterns from real-world video data. Reinforcement learning allows simulated agents to learn the best ways to navigate. And data assimilation techniques let simulations update themselves using real-time sensor data, moving us closer to predicting crowd movements as they happen. So where is all this used? Primarily in safety and evacuation planning for buildings and large venues. It helps urban planners design better pedestrian spaces and transport systems. Event managers use it to plan layouts for festivals and large gatherings. It even helps create realistic crowds in movies and video games. Of course, it's not perfect. Modeling complex human psychology, like panic or group decisions, is still tough. Getting good data to validate the models is tricky. And simulating millions of individuals takes immense computing power. Future work focuses on better AI, incorporating real-time data, handling diverse crowds with different abilities, and making simulations faster and more accurate. The ultimate goal is to create tools that help us manage crowded spaces safely and effectively in our increasingly populated world.